Hey y'all. So it was really fun reading over you guys' responses to that little rainbow question. Kind of cool to see where you guys are at with your current understanding. It's really pretty fascinating when you look at a rainbow, just how they work. They're really kind of magical things, and I really, to be honest, wasn't expecting to see one on such a kind of sunny, clear day. There were these little wispy kind of cirrus clouds that were moving across that maybe had something to do with it. I don't know. Maybe we'll find out. Looking through you guys' answers, though, a lot of similarities. Most of you guys mentioned something about light, which is good. But the question is, what is light? What is light? And that is where we begin kind of our discussion, our lecture today. So what is light? The things that we think of as light, kind of this visible light, it's just one type of this electromagnetic wave. There's many other different types. They form this thing called the electromagnetic spectrum. There's a whole variety, and visible light is just one little kind of slice, one section of that. But there's all these different types of electromagnetic waves. And to kind of go into that, I want to kind of refresh on what it means for something to be electromagnetic and what it means to create an electromagnetic wave. Now, you guys should recognize kind of those two root words for that, electromagnetic. We've talked already before about electric fields. And those are created if we have a stationary separation of charges. So if I had like a stationary charge particle, it would have an electric field around it, right? Which essentially just says if there's another positive particle next to it, if I had a positive particle and another positive particle, it'd push away. If I had a positive particle and a negative particle, they'd pull together, right? But when they're stationary, we have an electric field. Now, when those charged particles start to move, right, then we get this magnetic field, right? Which has a particular direction based on the motion of that charge. So that's how we have an electric field and we have a magnetic field. Now the question then would be, what would happen if I have a charge that is doing this? If we check this out here. So here I kind of I've got like this little marble, which is going to represent the charge. And I have it attached to a slinky. And I'm just going to, let me reel it in a little bit. Whoa, look at it go. So right now you'll see my charge is moving. It's going up and down, this kind of regular motion, right? But you'll notice there's a point at the bottom of its swing, right, where it comes to a stop. And it moves back up, and then there's a point at the top where it comes to a stop before falling back down, right? So here we have what's kind of called a periodic motion or a simple harmonic motion, something moving back up and down and oscillating. And its motion is actually changing this whole time. So this is actually a type of motion we'd say it's accelerated motion, right? This is a type of acceleration. So here, I have this particle, it's on the string, on this little slinky on the spring, oscillating or vibrating up and down, right? Back and forth. So I have a charged particle that's accelerating, it's oscillating. And so what does that mean? Right, well, in that case, I get what's called an electromagnetic wave, right? So a charged particle that's still, we get an electric field. A charged particle that's moving, we get a magnetic field. And if that charged particle accelerates, right, like if it oscillates or vibrates back and forth, then I generate an electromagnetic wave. I make a wave, which is so cool, right? And this wave, it travels through the medium, through something that's called the electromagnetic field, which you can kind of think is like this weird space. It's like this dimension kind of space that surrounds us. The electromagnetic field and this wave, anytime you have this accelerating particle, it generates a wave in that field that propagates in all directions, right? That wave always travels at the speed of light, right? That kind of speed is determined by the medium of the field. And it looks something like this, right? I have kind of a little visual of what that looks like here. It's animated, a little animated GIF. And what we have is we have an electric field, which is represented here in blue, right? And we have a magnetic field in red. And these are both oscillating, right, with each other, and they're perpendicular to each other, right? They're at 90-degree angles, and they oscillate, and that's what this wave kind of looks like. It's actually kind of oscillating, an oscillating electric field, an oscillating magnetic field, and that's what this wave is in the electromagnetic field. And so we can kind of talk about that, and we can kind of visualize it like we would with other waves. A way that you can kind of picture this, picture a wave, like we have this moving particle that's vibrating up and down. The way you can picture a wave moving and propagating through a field is, and you can do this at home, if you take a largish container, and so here I have a Tupperware of water. Right, we'll see if it'll focus on there. Maybe not. It's gonna have a hard time. Right, so I have my Tupperware of water, and if I have a charge here, right, that's oscillating up and down, right, I can propagate a wave. Right, so it goes up and down and propagates a wave. Pretty straightforward. And if I do it a bunch of times, then I can propagate like a wave that is kind of more permanent and more standing. Right? And if I let it settle again, the wave. And you'll notice if you look at it in kind of like slow motion, right? You'll notice and you can kind of see how the wave travels through that medium, right? It sends out kind of like a crest and a trough, and it actually like is this disturbance in the field from like this mean kind of flat kind of evenness. All of a sudden you get this ripple that forms through, and that's really what it is. Except for it's weird because an electromagnetic field, and it's kind of like space. It has it's multiple dimensions. It's in all directions. It's not just flat. It's actually like three-dimensional. But it propagates in the same way. So it's kind of a cool visual if you kind of do that at home and make some little waves. You guys can kind of see what's going on. Now, in order to better understand what we have really happening here with these electromagnetic waves, it's good to understand a little bit of background about just the fundamentals of waves and how we describe them and how they work. All right, so there's some general things that you should know about waves. For anything that kind of exhibits this simple harmonic motion, this back and forth vibration or periodic motion, we can model it using a sinusoidal curve, right? Not sure if you guys have talked about that in math yet, but it looks something like this guy down here. And so if we have a single kind of fixed point or an undisturbed position here, usually it's kind of like the x-axis, although not always. And on this x-axis, it can be either distance or it can be time. And then we have this kind of curve that goes up and it goes down, and it goes up and it goes down, it goes up and it goes down. So this kind of curve could be used to represent the motion of this little guy, right? Going up and down and up and down and up and down over time. Or it could be used to represent like a wave in water as it's traveling across a distance, right? And moving through space. Right, now there's a few things when we have this. One thing, there's some that we'll talk about more specifically, and there's some that I just want you guys to generally know. One is this amplitude, which is essentially the height of it that it's traveling from that median. So like in the case of this would be a small amplitude, right? Whereas if I release more, then that's a bigger amplitude, right? It's traveling more from its median point, which is where it would just hang normally, right? So there it's traveling a greater distance from that median point, right? And then here, it's traveling a shorter distance from that median point. Okay, so that's the amplitude. Same like with a water wave, like a small wave at the beach, small like one of those rollers that have a lower amplitude or a greater amplitude. A small one would have a small amplitude, and then a big one has a very large amplitude. The wave has a direction of travel, which is the direction it's actually kind of moving. So if I were to look at one single crest, which is what we kind of call these high points, if I look at one crest, that would be how that crest is actually, where is it actually traveling? So in this case, this crest would be moving in this direction, right? So we've got our crests, we got our troughs. And then the next big thing that we need to know, and this is one of the terms that you guys need to familiarize yourself with, is what's called the wavelength. And this is the distance, usually measured in meters, is the standard unit, in between crests of a wave. Right? Now we could also measure it in between troughs of a wave, or in between these midpoints, right? But notice here, if I go from here to here, that is not a wavelength, right? It's from here all the way to the same position on the next kind of wave. Okay, so that's the wavelength we measure in meters. So red light, for example, right, one form of an electromagnetic wave, has a wavelength of about 700 nanometers, right? So that's pretty small. That's 7 times 10 to the negative 7 meters, about 0.000007 meters. So if I have my trusty dusty meter stick here, right, this guy, oh, is it upside down? Oh, it's upside down. There we go. Right, so looking at this, right, this is 100, a single millimeter is 100th, so that'd be 0.01 meters. This is 0.0000007 meters. So picture just how small that wavelength is, right? That actual wave in that electromagnetic field is for red light. It's not very big, right? But that's actually, it's a measurable and is quantifiable thing, is this wavelength. Okay. The other thing would be frequency then. That's the other thing. Oh, by the way, we represent wavelength with this symbol lambda, right, which looks kind of like an L. But that's the symbol that we'll use for it. So if you ever see this, that's referring to wavelength. Then we have frequency, right? Now, frequency is the number of crests that pass a given point in 1 second, right? So if I have if I'm standing at one point, right? Let's say I'm up here, I'm standing right here, right at the top of this crest, and there's, I count for 1/1000. And at that point in time, there are 5 crests that pass by me, right? And that wave, right, would have a frequency of 5 hertz, right? Now, hertz is the measure of that we use for frequency. It's equal to 1 cycle per second. So if I have 5 hertz, then that's 5 cycles per second. Okay. So in order to know the frequency, right, I need to know not only, right, kind of the shape of my wave, but also how many crests are passing by at a given time. Right. We can also measure this. And once again, another example: red light has a frequency of around 4.3 times 10 to the 14th hertz. That's around, what would that be? So that'd be, let's see, thousands, millions, billions, trillions, 430 trillion crests per second, right? In other words, 430 trillion hertz, right? So that's red light. So that is a lot of crests, right, passing by every second. It's a lot. It's a whole lot, right? Now keep in mind the distance between those crests is incredibly small, but there's a lot of them passing by every second. And that brings us to our last piece that you guys for sure need to know for waves, which is actually the speed. And this is the rate at which a single crest, right, covers lateral distance over time. Okay. Also thinking of this as it's the rate at which the wave itself is actually kind of moving or propagating. So if we go to like an animated wave here, right, the speed would be the rate at which this kind of point here, right, is traveling, right, at which that crest is traveling through space, right? So let's say it's maybe going 1 meter per second, and that would be the speed of that wave. Okay. So we can calculate the speed. It's equal to the product of wavelength and frequency. So we can kind of write that in a formula. Speed is equal to wavelength times frequency. Speed is equal to wavelength times frequency. Now, like I said earlier, all electromagnetic waves, right, not just visible light, but all electromagnetic waves travel at the speed of light. Right? That's the speed of the medium of this electromagnetic field. That is the speed of that medium. And that's about 300 million meters per second, right? We represent this with the lowercase c. You guys are pretty familiar with that. And so we could actually write this as an equation, right? We could say c, which is the speed of light, right, is equal to the wavelength times the frequency. Right, and that's an equation that we can actually use to represent the speed of light. Right, so the speed of light is equal to the wavelength of that particular type of light, right, times the frequency of that particular type of light, right? So I will give you guys a little bit of a heads up. Not all wavelengths of light have the same wavelength, right? But they all have the same speed, right? So therefore, they can't all have the same frequency either, right? Speed is the one unifying thing for all electromagnetic waves. Their wavelength and their frequency varies, but the speed does not. Speed does not. So if we consider what this means for a second, let's say that you are, person standing here on this red line, right? Standing here on this black line here, and we've got all these different kind of electromagnetic waves that are moving by. And the one thing that you know is that each one of these crests here, boom, 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 they're all traveling at the same speed, right? Every single one of these crests. Now we could say, just in theory, that let's say that this is the distance, because of their speed, that's the distance covered by a single crest in 1 second, right? That's the distance covered by a single crest in 1 second. Well, that means that if you're standing here, after 1 second, what was here will be where you are. So if you were looking at this red kind of wave, right, that would mean that 1, 2, 3 crests would have passed by. Right, so here we'd have 3 crests. Right, on this orange one, we'd have 1, 2, 3, 4, 4-ish. Right, so there we'd have 4 crests. Okay, on this green one, we'd have 1, 2, 3, 4, 5. Have 5 crests that would have passed by. On this blue one, we'd have 1, 2, 3, 4, 5, 6, 7. 7 crests that would have passed by. Okay. And last but not least, on this purple one, we'd have, holy cow, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like 14. So we'd have 14 crests that had passed by. Right. So think about what this means. If we have a wave like this purple one that has a higher frequency, right? There's more crests passing by per second, right? Then that means, if we think about what light actually really is, right? That means that there's we can think of it as there's more stuff going on in a given second, right? There's kind of more excitement. There's more, maybe you could say change, right? Or the potential for change happening. And if you remember, that's kind of our definition for energy. So this gets into one of the big things, which is that light itself, right, is actually a form of energy, right? Light is just pure energy. It doesn't actually have any mass. It's just energy. And so this is one of the next questions that we're going to answer next time and try and understand now that we know a little bit more about waves. We're going to talk about, well, how do waves, right, like light, how can they be a form of energy? So how can light, something without mass, actually be a form of energy? How does that work? We're also going to get more into the electromagnetic spectrum and talk about what are these different types of electromagnetic waves that we can have outside of visible light. You know, what else do we see? What does it mean? Let's try and get some understanding of the relative scale of those things and why that is important. And so that's that. So a little bit of review, the things that you guys need to remember, right? If we start way back up at the top, right? Visible light is just one form of this electromagnetic wave. There's this whole spectrum of these electromagnetic waves, whole variety of them. Essentially, we have electric fields, magnetic fields. They're caused by charges that are either stationary or moving. If we accelerate those charges, then all of a sudden we get an electromagnetic wave, right? We get this disturbance in those fields that kind of oscillates and propagates through space. We can kind of define or quantify properties of those waves, such as wavelength, right? The distance between crests, as well as frequency, which is the number of crests that pass by a point in a second, and also speed, right? All electromagnetic waves travel at the speed of light, right, which is the speed of that electromagnetic field. And this becomes important because as we get into different types of waves, we'll start to talk about why those differences in frequency and wavelength become important, right? And also how they come about. So that's what you guys have to look forward to. And I will make sure you guys check out. I've got the kind of homework assignment posted here as well. I got some readings for you, got some practice problems. I got some questions to consider, and I will see you guys next time.